My talk is about very recent work, basically obtained with Professor Mirotin, who is here, and my student Evelyn Morales. But I will speak about maybe some more papers. Well, this paper that I saw, that I just mentioned, this one, the seventh one, it's under revision now. But basically, I will speak about the papers which are in bold. So we actually started the theory of so-called Hadamard-Berman operators with Professor Samko. Then we continued our study and studied Hölder spaces. And well, I think that there are some more very interesting questions in this object of mathematics. But let me show what I mean about this kind of operators. So I will call this one and this one Hadamard-Berman operator or Hadamard-Berman convolution operator. As you can see, there is a difference between these two operators, that you can have here variable what I have to here variable z, like so. Basically, I will call this Hadamard-Berman operator, and this one would be variable Hadamard-Berman operator. Okay, they are of interest in their own side, each of these operators. And of course, when you introduce a new class of operators, you first of all think what are the examples inside your class of operators, right? And of course, we have very nice examples inside of this class of Hadamard-Berman operators. First and basic example, the so-called projection, holomorphic projection, or Berman projection, or Berman-Jelbashan projection 2.3 operator that maps functions to holomorphic functions, like LP functions to holomorphic functions. It's bounded from LP to AP, which is LP intersection with holomorphic functions, at least for P between 1 and infinity, and it is an holomorphic projection. And this is a weighted holomorphic projection. It's not just because of mathematical curiosity that we put this weight. This weight is very important for studying holomorphic functions. The weight is connected to the boundaries. The weight of this kind, 1 minus z squared to the power lambda. It's obviously important when you study spaces of holomorphic function, and it has some connection with quantization also, and with many other things. Approximation, you can approximate using weight, letting weight going to infinity. You will get approximation, etc., etc. So it's not just curiosity. You just this weighted projection is very important as well. Both these operators are of this type, not variable. Both these operators are of this type. And of course, if you take two, basically I will speak not only holomorphic functions. Function g and f basically are measurable functions, first of all. But of course, there are some important examples and theories when g is holomorphic, for instance, and when f is holomorphic, or when both functions are holomorphic functions. And if both functions are holomorphic functions, then of course you have multiplier operators. So you have something like this: Sirius gn fn up to some mu n z to the power n. So the first operator here is nothing but a multiplier operator. You can think that, okay, we know almost everything, we know much of stuff about multipliers, about Taylor multipliers, about operator given by multipliers. So what's the point of studying this operator? But, and I am speaking about only the case when g and f are holomorphic functions. Otherwise, it's not true. But even if g and f are holomorphic functions, even in this case, it's worth to study these operators in integral form, because sometimes integral operators provide us with different tools of study that we can get rid of multipliers. For instance, when you study holomorphic Hölder spaces, when you study Hölder spaces, the theory of multipliers is useless. You can do very small things about boundedness or something using just theory of multipliers. So on first plane, in this case, in particular case of Hölder spaces, it's worth to study, to apply the theory of integral operators. That's why it's very nice to study operators even of this form in integral form. And if you go further, of course, this operator is not multiplier, because you won't have this type of formula even for G and F holomorphic. And here we also have another example studied by papers. I don't think that this list is complete, but here you can see the papers by Elman, Siskakis, etc. So they studied this type of Volterra operator, and it appeared to be a particular case of our general variable Adamar-Berman operator. You see, here it's written everything, so I will not read these formulas. You can see these formulas. But this is another example, another good example of operators in our class. And this gives an idea why it's important also to consider variable analysis, variable kernel. So basically, I will think, of course, you can think about this as a convolution, but we will fix a kernel G in what's following on, and F considering as arbitrary functions. Okay, one more example given by fractional integration of variable order. So this operator, also introduced in papers with Samko, is a so-called operator of variable integration. And it's very important when studying, again, Gödel spaces of variable order, because it has very nice mapping properties. I will speak about these mapping properties later. So this is another example. This particular case, when G, Z, W equals to this kernel, you have the potential, the variable potential. So there are some more examples, but maybe I stop on examples now and proceed further with the idea of study. First of all, I will speak about boundedness, and then I'll speak about application to study Gödel spaces. Okay, but maybe one remark about, I already told you that this operator is a multiplier operator, but even in this case, variable case, you can think about writing this as in a multiplier form, almost multiplier form, using these functions, gk, and these coefficients. So you can get this presentation. Of course, it's not multiplier representation, but still it may work for some purposes. And at least it gives you a proof of this symmetry formula. You see, this symmetry formula gives us ideas that we can think about this operator also as convolutions. Okay, and apply some ideas from theory of convolutions because of this symmetry formula 6.4. So actually you can put ZW bar here in function F, or you can put ZW bar here in function G, and it's not a problem that you have here Z also, not a big deal, provided function G and F are golomorphic function. F golomorphic in one variable and G is golomorphic in this W variable. Okay, so, and this also the point why we call sometimes these operators convolution operators. So, okay, let me show again these operators. I will speak about this operator or this operator in some different theorems, because for some results we can, for some ideas or results, we can obtain results for the general case, and for some cases we can obtain some results only for this particular case. Okay. Since I want to study operators in weighted Lebesgue spaces, that I need a definition of weights. And here we introduce so-called admissible weight. We say that a function that defined on the unit disk is admissible if it's kind of subjectivity property. If there exists a measurable function C acting from outside of the unit disk, such that this inequality is true. Okay, for Z and eta as written here. And we will call the function V a strong weight if you will have also the boundedness from below. Okay, so this would be for strong only, and if you have both, then we'll call this weight a strong, admissible strong weight. Okay, and examples of these weights, there are many examples here. I will not read everything. I will just wanted to know, to tell you that these weights, these very important weights, are here inside of this inside of these admissible examples. Comparing to this weight, we also compare our results when you insert some weights to this one, because as I said, this one are really useful for theory and for applications. Okay, so example how to okay, that would be theorem. The first theorem about boundedness. This is a general theorem. It provides us with sufficient conditional boundedness. Let us write this construction. Here is the upper bound for the admissible weight. And if this construction is less than infinity, that operator is bounded in LP, in weighted LP. And here we just calculated example. Okay, we give here also, we cannot use here the function g, but we can use the function given by supremum. And here, for instance, we calculated the supremum for the case of variable order integration operator. Okay. One more example. If you take the Volterra operator, then you can simplify your conditional boundedness because of these calculations, and you provide this constant. If this constant is finite, then the Volterra operator, studied by many people that I showed on previous slides, is bounded in weighted LP. Okay, so this would be another example as a corollary. And of course, if you have sufficient conditions, you wonder about necessary condition. As I said, it's not always true. It is not always you can get for a general case. Here I present only for non-variable kernel. So you remember this condition from sufficient condition of boundedness. So you can compare to the necessary condition of boundedness. So what you have extra, instead of upper bound, we have lower bound, right? Which is understandable. It's necessary condition. You have to estimate from below. It's understandable. But also you have some epsilon that kind of goes from the method of proof, and we cannot get rid of epsilon in general situation, but in some particular cases, when we restrict ourselves to some particular cases, we can get rid of this epsilon also. As shown in this remark, I will not comment on this remark, but sometimes when you go in details, in some particular case, you can get rid of some additional requirements. And one more theorem about necessary condition given for a variable, still variable function, kernel, but depends on only the angle variable, only the variable that runs over the circle. So in this case, we have this necessary condition, and I would like to comment that even though we have that, we don't have a condition for G, Z, W, instead we have condition for G, Z over modulus Z, W, but this still is okay, because in some important examples, for instance, when you study operator of fractional integration, you have this kernel 1 minus W to the power 2 minus alpha at the point Z, and actually if you write here Z over modulus Z, it's enough, because when people study variable analysis, they usually impose so-called Loch-Gölder condition on this parameter, and in many cases you can reduce the situation when you have here alpha of Z, you can reduce by some estimates, you can reduce to this operator. You know, in variable analysis, it can be done, provided you have a Loch-Gölder condition. So this still is okay. And the study of variable potentials, it's also important, because I think, okay, for instance, if you study problems, boundary value problems, and you impose some Gölder condition on the boundary, so why you don't impose one? You don't think that at every point you can have different conditions? Quite natural. I mean, if you impose on the boundary, I think that this is quite natural from the physical point of view, to have your boundary condition depends, that is a Gölder class depending on the variable of the boundary. Okay. Well, Actually, I also want to say that this operator appeared to be the best candidate for the so-called operator with homogeneous kernels. Actually, we have an idea we know the theory of operators with homogeneous kernels. It's a real theory. It's a real variable theory. We know many theorems, many issues, many facts about the homogeneous operators. But then we thought about what would be analog of the operators of homogeneous type of operators with homogeneous kernels in complex analysis, and I think this is the best example because it actually operator with homogeneous kernel. It's -2, of course, homogeneity, -2, and 2 is dimension, real dimension is 2. Okay, so and this allows us to apply tools from theory of operators with homogeneous kernels, but I will not speak about this because I will delay my talk then. But just to mention that we have works and we have papers on when we apply a theory of homogeneous operators to these operators. Okay, well, some particular results. Then I will list some also particular cases. When you go inside particular cases, we can have more details, or you can get easier sufficient conditions. And this, you may consider these 5 points as examples of application of the general results. So for Vertit-Bergman space, of course, you have the same criteria, the same sufficient condition for boundedness. You only need to prove that your image is allomorphic. Okay, it can be done. And for Hardy space, you can see that the condition is very easy. You see just this condition, this is the sufficient condition for boundedness in Hardy spaces. Let me not read the definition of Hardy space. I think that everyone knows in this room. So in that case, we can easily get, even for this general operator, for this general variable operator, the boundedness condition is like this. Just supremum belongs to L1 with respect to the measure mu. And measure mu, I didn't say it, but measure mu is arbitrary Radon measure. Okay, this is the example. Once we have this condition, then for instance, for this variable potential, the condition is quite nice, I mean quite simple of boundedness. This is an example, another example. And block space, actually little block space, again the same condition for boundedness. And little block space defined by this norm functions allomorphic in the UDDs for which this norm is finite. Okay, same norm, sorry, this norm. Okay, and +1 condition for little block space. Let me skip this. And actually, let me skip some slides. Actually, again, when instead of arbitrary Radon measure, you take just Lebesgue measure, and if you study in unweighted space, then we can prove a better result, so-called Young's theorem, not only LP boundedness, but the analog of Young's theorem for the operators. I guess that this can be proved for a more general case, but in just kind of time, maybe we'll think about this in the future. Okay, but at least in this particular case, you go into the more narrow cases, you have we have wider results. You have better results. Okay, now what time I still have?
10 minutes.
Okay, it's not so much. Okay, now I'll speak about variable Hölder spaces. Let me skip this. Again, potentials, even we can consider more general potentials, weighted potentials. You can split into series, but of course it's not power series, it's kind of function series. And once I want to speak about the Hölder spaces, I need the definition, because our Hölder space is defined with respect to modulus of continuity. So I have here the most general case, variable modulus of continuity. You can see the requirements almost the same as for regular modulus of continuity, but with only restriction that everything is uniform in parameter z, in variable z. So we define the local modulus of continuity by this formula. And this would be Zygmund type conditions for this variable case, very well known Zygmund conditions, but just here instead of usual modulus you have variable modulus, and here instead of constant you have variable delta of z, etc. So if a modulus satisfies to this condition, I will call it by z double with upper index first condition, z with lower Zygmund with lower index second condition, the intersection by Restechkin class. Okay, so the Gölder spaces is defined in natural way by using modulus of continuity. The norm, the semi-norm and norm are given by these formulas. But also, this is kind of classical Gölder spaces. Also, along with these Gölder spaces, we study the so-called Besov Gölder spaces defined in terms of behavioral derivative, and the semi-norm and the norm defined like this. And actually, when you study holomorphic functions, this space is very useful. First of all, because in many cases, in most of the cases, these are the same, like B omega equals to A omega. And usually it's better to consider B because you know how to handle with analytic derivative, with derivative of analytic function. You can have representations, etc. So you can have estimations very easy. Okay, so these are conditions when one goes to another, one embedded to another to second one to the first one. But basically, if the both conditions, Zygmund conditions satisfied, then they are the same. So you can think that this condition, just to explain you, if you think about regular Gölder spaces with parameter lambda, then this would be this condition. So lambda is not 0, neither 1. Okay. So let me skip the slide. Oh, actually, you can just compare. Again, the theorem says that you can just compare the Gölder density on the boundary. Okay, so I have two different cases. I will have two separate cases. Let me write Bergman projection operator. Fw, just in the easiest case, zw bar squared daw. This would be Bergman projection. It maps functions, Lebesgue functions to holomorphic functions. When you subtract alpha, then you have potential operator that improves function. When you add alpha, you'll have differentiation operator, right? When alpha is 0, you have just projection, just singular operator. But what happens when you put here z? Then at some points, alpha can be 0. And what is going on when alpha goes very close to this line? When alpha is almost E theta, right? From one side, it should be projection. From other side, it should improve some property of functions, right? So this is a very interesting idea. And actually, when studying this idea, we split two cases. In the first case, in this case, we allow degeneracy. This means that we allow alpha to be real alpha. I don't care about imaginary part of alpha, right? It's clear. I care about only real part of alpha. Okay, so in this case, I allow a real part of alpha be also at some point z, not at all points. At some point z be 0. So here I have a general operator, which is a generalization of fractional operator. This is characteristic. This means for this operator, this means that this characteristic behaves as a constant, but don't mind about this. Just in this case, just I told you that we allow alpha at some point it improves function, at some point z leaves function alone, like as it was. It's very interesting. But instead, when you allow alpha to be like this, you have to input some additional requirements, on modulus of continuity, defining the spaces A omega and B omega. And in this case, let me see. Okay, we have a general result for this operator. We have very strict conditions on modulus of continuity, and we have boundaries of this general operator in these Bezos spaces. And because we imposed very strict condition of modulus of continuity, they are so strict, so we have that B omega coincides with A omega. So in this case, makes no sense to study separately A omega, okay? Because the conditions of modulus, we allow alpha to be arbitrary, but instead we have to impose conditions of modulus of continuity to have the result, okay? Otherwise, if we don't allow alpha to be 0, real part of alpha to be 0, then we can lose conditions. We can allow conditions to be mild on modulus of continuity. We need this kind of Zygmunt type estimate for modulus of continuity of potential operator. You can see how it, incorporating this infimum, how it goes into the Zygmunt estimate, and from this Zygmunt estimate, it's easy to obtain boundedness condition, and this does not permit us to allow alpha to be, real part of alpha to be 0, but instead we have very mild, just one condition, Zygmunt condition for modulus of continuity. And of course, I already mentioned that we are away from 0 and 0.1. And in this case, as I said, it improves, of course, the Gödel spaces. So it acts from A omega to A omega alpha, where A omega alpha given by this modulus of continuity. So you have old modulus, the first modulus of continuity, you multiply by this classical h to the power real of alpha. Okay? And maybe I skipped some slides. Maybe I was too fast, but at least I guess I finished. Yeah.
Thank you very much.
Thank you.